Okay, we're in section 20. This is the review. And in the review section, what we do is we go through what we just did with series, right? So convergence or divergence of a series. We go through this over here. We talk about convergent properties of series. We talk about geometric series. You'd be familiar with that. A P series. Yes, you'd be familiar with that at this point. Divergent test, integral test, comparison test, limit comparison test. Yeah, I know it's a lot of material, by the way, right? AST, alternating series test, ratio test, root test, right? Then what do? We go for examples, all right? So what I'm gonna do is switch to the whiteboard and I'll go through the examples. Not that I wanna go through every example, but when I say every example, I'll certainly talk through every example. I realize in the blue area, there's sufficient work down there for understand, but I'll talk through each of the examples for you. So let me do a new share. And there still will be homework on this as well. It's a review. All right, so let's go for this over here. And as I'm doing this over here, my goal here is, one is to understand, and then, two is to, can I figure out what they want me to do? So they say test the series for convergence or divergence. All right. So, one thing you could do is, there are many things you could do, but the bottom line is, one thing I would probably do right from the get-go is look at the limit as n goes to infinity of the an, which is 1 over 2n plus 1. And what would that give me? That would give me 0. Unfortunately, this really doesn't tell me much, right? Although the limit 0, it doesn't tell me anything about the convergence of the series. So the next thing I would look at is, basically, I guess, maybe limit comparison test. So I'm wondering, what would this compare nicely to? And I'm going to say maybe this thing sort of looks geometric. So I'm going to use what's called the limit comparison test. And I'm going to compare this with 1 over n, and n equals 1 to infinity, which I know is a divergent series. That's harmonic. All right, so let's do the limit comparison test. I'll write this down. And again, you have this in the notes, the limit comparison test at this point. Let's write this down. Limit as n goes to infinity. And this is always tough for me to write down, but I'll write it down. And what am I going to write down? I guess an, which is that 1 over 2n plus 1. And I'm comparing it to this over here. Well, I got to figure that one out, right? So limit n goes to infinity. Well, I got to make that a little better looking, don't I? So it's going to be n over 2n plus 1, which is equal to that limit divided through by n, you get a half, right? And that's certainly a finite number greater than 0. So what do I know? I know my original series by the LCT test is divergent. So I know this is divergent. All right. Are there other ways to do that problem? Of course there are. There's other ways to do it. All right. So I'm going to say, it's all typed up for you, yada, yada, yada. So let's take a look at this one over here. And again, I'm going to, try the first thing I would probably always try. It never productive, by the way, but it's so easy. I want to try it. N goes to infinity. And let's see, -1 to the n, and then I get 2 to the 1 over n. That's the nth root of that. If I'm looking at that, 2 to the 1 over n, that's going to go 2 to the 0, which is 1. So what happens, this thing is going to bounce around between, -1 and 1. What does that mean, DNA? Well, you know what? This paid off. I'm glad I did this. What do I know about this? This is divergent. What test am I using? I'm using the test for divergence. The first thing I looked at, probably the easiest thing to do, by the way. All right. So it diverges by the test for divergence. Let's look at this one over here. This is an alternating series. Right? It alternates. And let's just take a look at that. It is an alternating series, And what do I want to do? Let's take a look. A limit n goes to infinity. This is the an in the problem, by the way. Root n plus 5. What would that give me? That would give me 0. And what else do I want to do? I want to show that the thing is going down, which means that AN compared to AN plus 1. Now, this might be tough to do, but I think I can handle it. And what would you get over there? Let's take a look at that. What do I want to happen? I want the AN to be this. All right. Let's write this down. So it's going to be root n plus 5. And these are positive term series, by the way, at this point, without the minus 1 in it. And what do you get over here? What do I mean by that? This is positive, always positive. And then I get root n plus 1 over n plus 5. All right. Let me see if I can handle that. That looks pretty tough though, doesn't it? So it's going to be, let's see, I got to do some work over here. So root n plus 5 greater than n plus 5. You know, this inequality looks like it might be too much work for me. So I'm going to say, I don't want to do that. I want to do another way. All right, let me get my eraser out. And I'm starting to think this is just too much work for me. And I'm a little tired. So I'm thinking maybe I can show this another way. And a way to show this another way is just, maybe look at a continuous function and find out where it's decreasing. All right. So really, what is this thing saying? It's decreasing. And let me see if I can do that. So I would say, a continuous analog of this would be root x over x plus 5. I would look at its derivative. Again, if this is too much, I'll think about something else. Let's see, x plus 5 squared, x plus 5 times 1 over, the derivative top is 1 over 2 root x, minus the top, which is root x, times the bottom, which is 1. Well, I got to do some work over here. I'm going to multiply top and bottom by root x. Again, you may do something different if you like. And what would you get on top? I'm going to do 2. You would get x plus 5 minus 2x. I hope I didn't make any mistakes here. This would be 5 minus x. And what do you get there? 2 root x, x plus 5 squared. All right, so what'd you do all that work for? I want to find out where it's decreasing. And by the way, I want to claim to you, this thing is only starting at 1 forward. That's all I'm looking at. So I'm going to start at 1 forward. And where's the critical number 1 forward? Not 0, not minus 5, but at 5. So what number would I pick after 5? I don't know, 10. What would this turn out to be? Negative, which means it's decreasing. A number before 5, what would that be? I don't know, 4. That's going to be positive. So this thing is decreasing. I'll write this over here. And I got to split it up. N equals 1. I'm going to go up to 5. And it's going to be minus 1. N, root n, n plus 5, plus, by the way, I could have picked 4, but I'm going to pick 5 because I like that 5 number. N equals 1 to 6 minus 1n, root n, n plus 5. This thing is definitely a finite number. It's a finite number of terms. I could add that together. No problem whatsoever. I'm going to use the AST in this. What do I know? The limit, I'll write this down now, as n goes to infinity, of root n over n plus 5 is 0. That's one condition that needs to be met. The other condition I'm going to state it because I know it from this over here. I'm going to state that a n plus 1 is going to be, you know what? I'll do it in the same order I did before. Let me get my eraser out. That a n and n plus 1. What do I know about this thing over here? It's going like this. And that's 2 conditions I need to clip off. All right. So this series over here is convergent. All right. Let me go next page, see if they've done anything weird on that. And let me just say, I just say better than 5. Yeah, they did the AST. They didn't write much work down there, by the way. All right. But they use the AST. I put all the work down there for you. All right. Test the series convergence. Divergence. Oh, boy. Another problem, don't I? Well, I guess I'm just going to use the AST. All right. And let's write that down. So limit, again, I'm using the A as T. The limit as n goes to infinity, n squared plus 2 equals 0, condition met. What else do I need to show? I need to show that an plus 1, I need to show this over here. I think I can handle that. So what do you have here? N squared plus 2, and that would be n plus 1 over n plus 1 squared plus 2. I want to point out these things are all positives over here, everything. I'm not going to worry about like anything I did in Math 119 with, sine analysis, because everything's positive. So let's do this now. Let's see if I can figure this out. So you can get n times n plus 1 squared plus 2n. Oh boy, it's going to be a lot of work. And what do you get over here? N squared plus 2, n plus 1. Before I move forward, I want to make sure I did that right. So n times n squared plus 1 squared plus 2n. N squared plus 2 times, yeah, I got to do some work over here. N squared plus 2n plus 1 plus 2n. Boy, more work. N cubed plus 2n squared plus n plus 2n. At least work I can do, I'll tell you that. It's going to be n cubed plus n squared plus 2n plus 2. Let me write that down for you. Let's see, subtract this from both sides. This would give me n squared. I'll write that down. This would be minus n. I'm sorry, not minus n. It will be plus n. And now I'm going to put this over here. All right. Is that true for all n? Let's see, I could start at 1, right? What would I get? 1 plus 1 is 2. That works. And then I get, yeah, true for all n. All right, so that's true. Let's go back over here. I think I might have made a mistake because they said n greater than or equal to 2. Why would they say that? Maybe I made a mistake. Let me go back over here and see if I did this right. n squared plus 2, n plus 1 squared plus 2. Let me go back over my work. And I got to make sure I did it right. And what do you get over there? Let's see if I did that right. N times n plus 1 squared, I got that. 2n, I got that. N squared plus 2 times n plus 1. I did that. That's n squared plus 2n plus 1. I'm just checking my work, by the way. So n cubed plus 2n squared plus n plus 2n. That's going to be n cubed plus n squared, 2n plus 2. Yeah, I got that. Let me just do this again. And let me see, that would be n squared. That's okay. I see that. And then if I subtract 2n, that disappears. So plus n. I see that. Yeah, I'm going to say it's true for all n. The fact that they said it's true for n greater than or equal to 2, that's fine as well. But it's true for all n. All right. But it passed the AST test. All right, let's go to the next one. I'm kind of looking at it. Well, it really does look nasty. So I'm going to look at it. And I'm not going to get the limit because the limit of that, the nth term is 0. And so I'm going to look at, maybe, I don't know, maybe some kind of like a comparison here. So let me see, is it a positive term series? So if n starts at 1, well, it sure does appear to be a positive. I think it's a positive series. How do I know that? The cosine's being squared, it's always a positive number, or I should say non-negative. So let's look for a comparison. Let's write this down. Look for a nice comparison, this one over here. And I'm going to say the cosine, the worst it could be is 1. So I'm going to say that maybe this compares nicely with 1 over 2n. All right. Now here comes my problem. That which one's bigger? I gotta say this, but let me make sure that's the case. I'm gonna write this down now. I just want to make sure this is true. It's all positive though, so I don't have to worry about this, negative signs or flipping the inequality. And you get n plus n cosine squared n. And then you get n greater than or equal to n cosine squared. I'm sorry, I put an X there. I'm so used to writing that down. I got to think for a second. I'm going to agree that's true. And why is that? N is always going to be greater than or equal to n times the cosine squared of n. Why is that? The most the cosine squared could be is 1. So this is fine. This is good. This is good. Now, what do I know? I know this is a divergent series. It's divergent, all right? It's related to the harmonic. So what do I know about this guy over here? This also diverges. What did I use? The comparison test. All right, let's see what they did. And they did conclude it's divergent, compares to harmonic, and they did say they mentioned a comparison test. Let's go to the next question. Clearly an AST. And let's take a look at the limit. The limit as n goes to infinity. And that's going to be what? N over n plus 2. Unfortunately, this is going to be the number 1. No good. All right, I'm not going to use the ST. I'm going to use the first test, which is the limit as n goes to infinity of that term, which is -1 to the n plus 2. And what's this going to be? It's actually dne. And why is that? It goes off to 1 or -1, so it's dne. So what can I conclude? The original series is divergent. And what am I using? I'm using the test for divergence, the easiest one to use, all right? Rarely works, but it's the easiest one to use. Let's look at this one over here. This is a positive term series. And I'm going to think about it, and I'm wondering who to compare it to. I'm going to say maybe it's geometric in form. I don't have much for a comparison, right? And I'll put 1 over 3 to the n. Let me write that a little differently. This is a convergent geometric series. So let's take a look. 1 over n plus 3n. I'm going to be comparing it with this guy over here. All right, which one's bigger? All right, I'm going to say it's like this. Let's put this down. 3n. I want to make sure this is true, by the way. Well, that certainly makes sense because these would cancel off. And I'd have n greater than equal to 0. And that's true because n starts at 1. So this is good. I'm going to my eraser out. And I'm going to say by comparison test that this is going to be a convergent series. So what do I now know? This is convergent. What was I using? Comparison test. All right. That's indicated over here. Comparison is written down for you as well. All right. More difficult. I'm looking at it. And I got to be really concerned about it. And let me just be really, really, really careful about this guy. I mean, I can look at the n goes to infinity on this one, that's 0, so I'm not going to bother with that. So I want to be careful, and I know the natural log would equal 0, right? When n is 1, right? Now they're starting at 2, so that's good news. So let me write this down. Natural log of 2 equals, well, let's say I don't know. Let's write this down. What's it going to be? Well, 2 would equal e to the x. Well, clearly I know it's a positive number. I hope you know that. All right. So I'm not so worried about it anymore. All right, let me erase. And this is a positive term series. And I'm going to look at it. And for comparison purposes, I really can't think of any good comparisons off the top of my head. So what are the tests do I have? I'm going to say integral test, but I'm not saying it's going to work. So I got to find a continuous function, f of x, that's continuous, positive, and decreasing. Let's take a look and do that. It's going to take a little work on my end. I'm going to write this over here. F prime. Oops, that doesn't look right. Is -1. Let's keep doing this. Again, I'm just doing some work over here. If it's unproductive, I'm going to stop. Times the derivative of the inside. Boy, that's going to be a tough one, isn't it? So the derivative of x is 1 times the root of ln x plus x. That's going to be a tough one. It's going to be 1 over 2 root ln x. And the derivative of ln x is 1 over x. I got to keep writing this down, by the way. And I know it seems like a lot of work. We're encouraging work, by the way. What does this give us? 1 over 2 root ln x. Oh boy, let's take a look. I know it's a lot of work. Let's see, I get 2 ln x here, plus 1. All right, let's take a look. Oh, by the way, my analysis is only on the interval from 2 to infinity. That's good news, all right? So let's take a look at one at a time. Now I'm looking for critical numbers, and certainly someone says, oh, x is critical. It's not critical. It's not in the domain of the problem. So the only thing I really have to worry about is this 2 ln x. When is it -1? Let me write this down for you. We're going back to mth122. This is -1/2. And what do you get over here? X is going to be equal to e to the -1/2, which is 1 over the root of e. Well, I hope you know that number, whatever it is, it's nowhere near the number 2. It's much smaller than it. So I'm going to say this thing is always going to be negative. It's always negative on the interval. What am I really talking about 2 forward? So 2 forward, this thing is always negative. It's going down. So someone says, you spent so much time just showing that thing's going down. You're not kidding. All right. So I know I got a positive term series that's decreasing and continuous on the interval from 2 to infinity. So now you got another problem. Can I integrate it? I have no idea. Let's write this down. So I'm going to go to, I'm using the integral test, by the way. 2 to infinity. 1 over x root ln x dx. You know what I'm going to do? I'm going to do that on the side. I don't know if I can do it. I don't even look at that guy. Let's try ln x, right? Looks pretty bad. I'm using u substitution, by the way. Du is 1 over x dx. Wow, this can look like a miracle. What do you get over there? Well, I got this here, which is du. And then I get 1 over u to the 1/2 power is going to work out like a charm. That's u to the minus 1/2 du. This is a star. So I'm going to put u to the half. And then it's going to be, I divide by half and multiply by 2. And that's plus c. I'll put that over here. And what's that going to be? 2 root, what's u? ln x plus c. So let me go back up here. I got it. I'm going to write this down now. So what's this going to be equal to? Limit. I guess we're going to say a goes to infinity. Oh, I forgot. 2 root ln x. Limits of integration would be 2 to infinity. Hope you guys are okay with that. Hope I didn't make too many mistakes. And what's that going to be? Infinity. So what do I know? This guy diverges. All right, let's take a look at this and see if we did. Yeah, they got all the work done. Not exactly the work, but they got the truncated work down for me. And I feel good about it. All right, let's go to the next one. And again, I know it's tough. I find this stuff difficult too. All right. This one over here, I'll be honest with you, I always have trouble with this. And what I mean by trouble with this is just getting the proper test for this, but this doesn't look like it's going to be like an integral test. It's got a factorial in it. I know it's positive term, by the way. I guess the only thing I really could do is maybe I could do the ratio test. All right. And I gotta say, the only thing I can really think of off the top of my head is ratio test. All right. Let's take a look at that. And I got to write this down now. So limit n goes to infinity. I'm not going to put the absolute value symbol down. The reason I know that every single factor in the problem is going to be positive. So I'm not worried about, are there negative numbers in this problem with the absolute value? Ratio test has an absolute value in it. So let's write this down. So it's going to be n plus 1 factorial. I'm writing down n plus 1 now. And this is going to be 2 times 5 times 8. Yada, yada, yada. Well, you get 3n plus 2. What would the next factor be on that one? They appear to be going up by 3, right? So the next factor, if it goes up by 3, would be 3n plus 5. Now I'm going to divide by an, and that's like multiplying by its reciprocal. Well, that's going to be n factorial. And then you'd have 2 times 5 times 8 times yada, 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 3n plus 2. Well, this works out pretty nicely. I'll tell you why. This nightmare disappears. And this nightmare almost disappears. It becomes n plus 1. So this limit turns out to be this. N plus 1 over 3n plus 5. What do you get over there? 1/3. All right. And what do we use a ratio test? This is less than 1. So what do we know? It's convergent. All right, not bad. All right, so the next one. It's an alternating series test. Let's see if we can do the AST on it. I don't know. I'm better going too forward on it. All positive. That's what I mean, that the AN in this problem. I'm not looking at the alternating pattern to it. I'm just looking at this over here. But let me write this down over here. Limit n goes to infinity. 1 over n ln n. That equals 0. I'm using the AST. What else do I need to show? I need to show that that it's decreasing. All right, so I need to show that AN, that might be tough to do, but let's take a look, see if we can do it. I need to show this, and let's see if I can do that. Well, I'm going to say it's pretty obvious, actually. And how do I know that? I'm looking at the bottoms. Let me just write this over here if it's not that obvious. What do you mean obvious? For the numbers that we're dealing with, 2 forward. So 2 forward, I'm going to say clearly this is going to be bigger than that 2 forward. All right. Just look at the product. It's going to be the natural log of, like if it did 2, that would be 3 and that would be 2 on the other side. Clearly the case. All right. So I'm going to say AST works fine. All right. So what I'm going to say, series converges. We use the AST. All right. This one over here. I'm looking at it again. I have to be honest with you, that they really look like they might be difficult to do. But here's the problem with this one. I'm looking at it, and certainly I know at 1 the thing is 0, and then after that, like when I go to 2, it's all going to be positive terms. All right. Now I don't want to sound retentive to you, but I'm just going to make sure you know that this is the same thing as this over here. Now, someone could say, do you really need to do that? No. Now, someone says, why'd you get rid of the 1? The 1 gives me a 0. But now, once I get to 2, it's a positive term series. So I'm looking for a comparison. So if I thought about the top, the square root of n squared, when you get in a really long term, the minus 1 doesn't play much role in it. So I'm going to say the top sort of looks like n. And the bottom, the guy that's on the bottom really looks powerful is the n cubed. And what is this thing over here? I'm going to say a nice comparison would be 1 over n squared. So let me write this down for you. So what do I know? I know n equals 2 to infinity 1 over n squared is a convergent p-series. Yeah, that's something we should know about. Then what am I going to do? I'm going to do a comparison test. See how I can do it. Let me write this down. You could do limit comparison test too if you want. You know what? I may go to limit comparison because I don't know if I want to solve that inequality. Yeah, it's too much for me. I don't want to do it. I'm going to do a limit comparison test. LCT. Limit n goes to infinity. I'll write this down over here. N squared minus n cubed plus 2n squared plus 5. And then I'm going to divide by 1 over n squared, which is reciprocal. So I'm going to put n squared over 1. Got to do some work. And I'm going to say the highest degree variable. And this might seem strange to you, but the highest degree variable is n cubed. N cubed, when you go towards infinity, is the same thing as saying the square root of n squared times n squared. And that's true for positive numbers. So I'm going to divide the bottom by this, and I'm going to divide the top by that. And let's see what happens. And the bottom's really easy, right? What do you get? 1, I'm dividing n cubed in the bottom, plus 2 over n plus 5 over n cubed. That doesn't look like a cube, does it? Let me clean that up a little bit. I'm going to the top by n squared, root n squared, so I would get, times 1, and this root would look like this now, 1 minus 1 over n squared. And what do you get there? Well, you get a finite number. You get a limit of 1, right? It's a finite number, right? So what do I know? Convergent series. Let me make sure that is 1, by the way. 1. Yep, limit's 1. So I use a limit comparison test. They just did a comparison. I didn't feel like doing the inequality, by the way. So I used a limit comparison test. And my conclusion is that it's a convergent series. Okay, let's do the next one. I'm going to say, let's take a look at that. And I'm glad they're starting at 2 because then it makes it easier for me. If they started at 1, I'd have a problem with that because it's not defined at 1. And let's write this down. So I'm going to use AST. I'm going to look at the limit as n goes to infinity of 1 over root n minus 1, and this equals 0. That's good news. And now what I'm going to do, I'm going to see if I can show this, right? So I'm going to see if I can show that an is greater than or equal to an plus 1. Let's write it down. Whether I think that's obvious or not is incidental at this point. Make sure, I'm going to make sure I copied this correctly first, so I'll do that. I did. Okay. So what do you get over here? Well, I'm going to say for positive n, that's clear as day to me, all right? That this is definitely larger than that, okay? So I'm going to say this has been met. So what do I know about this thing? This converges by the AST. Let's go to the next page. They did go on to say that converges by alternating series test. Yeah, did all right. All right, another nightmare problem for me. And I got to look at it. Oh boy. Let's take a look at it. I gotta be careful about this. The n is positive, right? And the sign of 1, let me put out what I mean by that. The sign function looks like this. And if I do 1 over n, I want to point out this is pi over 2 here, and 1's over here, positive number. Oh, it's a positive term series. This is nice. Let me get my eraser out. All positive term. So I'm gonna, I don't know if I want to do a comparison at this point, but let me just look at the limit. Who knows? And this looks like it's familiar to me. I'm going to say n times sine 1 over n. And what I'm going to claim over here is, I think we've seen limits in the past like this. Now I'll tell you the big one that you've seen in the past is this one over here. I think we've seen that one in the past. So someone says it's not the same. It's not the same. I'm not saying it is. Keep that in the back of your mind though. The limit n goes to infinity, sine 1 over n, 1 over n. Well, I'm going to claim it's really the same thing as this one over here. Which is 1. What I want to tell you about what's open over here, I'll point it out to you. As s goes to 0, that argument and that argument needs to go to 0 at the same rate, and it does. How about when you go towards infinity on the end? This goes to 0 and that goes to 0 at the same rate. So you're left with the same limit. What do you get over here? It's still going to be 1. All right. So what do I know about this thing? Test for divergence. This series diverges clearly. All right. All right. Let's do this one over here. I'm kind of looking at this. Boy, it's right to the other one, isn't it? It's a positive term series, right? It's a positive term series. And I'm going to say, I'm going to use a comparison test on it. If someone says, why are you choosing 1? I know 1 is greater than sine or equal to it of any number. So what do I know now? No, I'm not going to use a comparison test for that because I don't want to do this thing. But I do know there's a comparison between the two, right? But the limit comparison test would be good, but the comparison test would be bad. So I'm not going to use the comparison test. I'm going to use the limit comparison test. A little bit easier for me to do. Let me write this down. So limit I really have to think about that too if I want to do that. And that's going to be another problem for me. So the limit comparison test then goes to infinity. That's not going to work out either. Let me erase. That was a good try. I keep thinking about it. I don't want to use 1 over root n. So I'm going to say sine 1 over n, roughly speaking, as you go out towards infinity, is just like 1 over n. Right? What do I mean by that? The sine curve, you looked at it. Right? Sine curve looks like this over here. So near the origin, like when you get close to 0, that the sine looks just like the line y equals x. So I'm going to write that down. So I'm going to say, as a comparison, maybe I could do this. It's sort of like this for comparison reasons. But I don't want to do an inequality. It's not going to happen. Right? So I'm still going to go for the limit comparison test. But this guy looks really bizarre to me. Like I said, they're roughly comparable. Like when you go towards infinity, these two will look just like one another. They really will. So what do you get over here? This would be 1 over, what would that give you? Let me write this down for you. It's a little complicated, isn't it? It's 1 over n. That's root n. So I would say this is 1 over n divided by root n, which is 1 over n times 1 over root n, which is 1 over n to the 3 halves. Okay, so I think I'm ready. So I'm going to say this guy over here. For comparison purposes, it kind of compares to this one over here. And I know this over here is a convergent P series. I'm still not out of the woods yet. I'm using the limit comparison test. Let's write it down. Limit n goes to infinity. Sine 1 over n root n. I'm dividing by that P series, which like multiplying by reciprocal, and 3 halves is root n times n. Hey, this looks like the past problem. What do you get over here? Limit n goes to infinity, n times sine 1 over n. I'm going to write this a little differently. I know we just did it. I can't do it. I can't have to do it again. This is going to be sine 1 over n, 1 over n, and that limit over there is going to be 1. All right, so we did it right. Let's go back over here. And they did a limit comparison test too. And they got that. What do we know? Series converges. All right, let's do number, oh boy, this looks like another tough one. So let's see, test a series for convergence. It's positive term series. And let's take a look at it. definitely positive term series. The limit as n goes to infinity would be 0. I'm not going to look at that, of that term. I'm going to try the integral test. All right, let's write this down. F of x equals x squared plus 1, 5 to the x. And let's take a look. I'm going to say it's definitely positive. I wonder if it's decreasing everywhere. Let me just take a look at an example over here. So if I put 1 down, what would I get? You know, let's take a derivative. Can't have to review derivatives, right? Well, x squared would be 2x, right? Now I got a problem. What's the derivative of 5 to the x? Let me write this over here for you. If y equals 5 to the x, take the log of both sides. Take its derivative. That would be 1 over y dy dx equals ln 5. And dy dx would equal y, which is 5 to the x times ln 5. Let me write that down. It's tough. I'm not saying it's easy for you. I can divide top and bottom by 5 to the x. And what do you get? 2x plus 2x ln 5 over 5x squared. And I'm going to factor 2x out. And what do you get? 1 plus natural log of 5, 5x squared. Did I make a mistake somewhere? Oh, I know I made a mistake somewhere. I'm sorry about that. So I have to, the reason I'm looking at it, it just doesn't make any sense. Sorry about that. This here is negative. And I'm only analyzing this, let's point this out, from 1 to infinity. So this here is always positive. So this thing is going to be decreasing on the interval. So what have I found out? That this is going to be positive, continuous, and decreasing. Here comes my trouble. Can I do the integration? And I'll write it down for you. And I hate doing it, to be honest with you. But 1 to infinity, x squared, 5 to the minus x, plus 5 to the minus x dx. All right. But I want to go to the next page to see if they did the integral test, because maybe I'm barking up the wrong tree. You know what, they use the ratio test. I'm not going to do the integral test then. I'll just do the ratio test. Because I believe the integral is doable, but it just seems like I'm going to be going through this derivative things over and over again. Let's just use the ratio test, all right? RT. I'm not going to use the absolute value. They're positive terms. So you get n plus 1 squared plus 1, 5 to the n plus 1. I'm dividing by an, so it's a reciprocal, 5 to the n. And what do you get at bottom? N squared plus 1. I got to do that. And let's see what happens. Let's see. You get n squared plus 2n plus 1, which is 2. You get 5 on bottom, because one of the 5n cancel off. 5n squared. Let's see. Plus 5, right? What's that limit? 1/5. So what do we know? Certainly a number less than 1. So by the ratio test, we know this is convergent. All right. By the way, I gave up on this end over here because I realized that doing an integration, I gave up. It just seemed like it gets toward the end of the problem set. and I got tired. I didn't want to do an integration. I'm not saying you can't do it, by the way, but it's convergence series. So next page. And this one over here, I don't know. I'm looking at it and I'm going to say, I'm going to look at the limit. And the reason I say that, I'm looking at it, I how to do that problem, but what I do know about it is that the top looks like it's going to be much bigger than the bottom at some point. So I'm going to look at the limit. It's positive term series, by the way. N goes to infinity, 5 to the n, 3 to the n, plus 4 to the n. I'm going to divide top and bottom by 5 to the n. I don't know what's going to happen. 1, this would give me 3/5 to the n plus 4/5 to the n. Well, you know what? These are all proper fractions now. So what's on the top is just going to go to 1. This will go to 0, and this will go to 0. So what do we get? 1 divided by, it's a finite positive number, but they're going to go towards 0 from the right. Just going to get plus infinity. So what do I know? By the test for divergence, the series diverges. Test for divergence, again, infinity. All right, so what are you doing now? And I know it's tough. You're going to do this. Are you going to get stuck? Of course, you're going to get stuck. When do you want to get stuck? When you're doing homework, not when you're on the exam. When you're on the exam, though, you're still going to get stuck sometimes. If you get stuck on the exam, my suggestion is concentrate on what you can do. Then come back to what you can't do. Everyone gets stuck, including me.